Welcome to Berkeley City College, and without any further ado, I would like to introduce Dr. Richard Karp. Thank you.
Thank you very much, Debbie. I'm the director of an institute that was founded about 2 years ago called the Simons Institute for the Theory of Computing. Among the things we do in particular is outreach to the public to inform the public about interesting developments in mathematical and computational sciences. And our cooperation with Berkeley City College through Debbie and with MSRI through David Eisenbud and his staff has been a great pleasure. This is the third in the series of 7. This is the third one that our institute has been particularly involved in. Just a word about the Simons Institute. We study fundamental problems about computation that arise in a diverse set of areas, partly in computer science itself and information technology, but also some of the problems arise in mathematics, in the physical sciences, the engineering sciences, the social sciences, and even in the world of commerce. So we take a very broad view of our field, and this is likely to be reflected in some of the future programs that we run for an audience like yourselves at this very nice venue. We're very happy to have Michael Sipser as our key speaker, our main speaker today. Mike got his PhD from Berkeley in 1980 in our theoretical computer science group. He spent the bulk of his career at MIT as a professor of mathematics, as chair of the mathematics department, and most recently as acting dean of science at MIT. He's a great expositor. He's written a wonderful book in theoretical computer science. He's proved wonderful theorems, and I think you're going to enjoy his talk. The title is Beyond Computation, the P versus NP Question.
First, thank you, Dick, for the introduction, and I want to thank Berkeley City College for hosting us, and also the Simons Institute for Theoretical Computer Science, and the Mathematical Sciences Research Institute for sponsoring this event. And most of all, I want to thank you all for coming out here on this beautiful Berkeley evening to come hear a talk about mathematics. Because that's what we're talking about today, is mathematics. It's theoretical computer science. It's talk about computation and the limits of computation, but it is also a mathematical talk. And not only am I going to talk about mathematics, but I'm going to tell you about a problem that I don't know how to solve. No one else does either, for that matter. But maybe that's why you're here, because it's those unsolved problems, unsolved questions, unanswered questions, the open questions, as we like to say, that often are what are most inspiring to our curiosity. So I'm going to talk about a problem at the crossroads between mathematics and computer science called the P versus NP problem. And by the way, even though it's a math talk, I'm going to hopefully make it accessible to everybody. And if I don't, if you get lost, well, it's my fault. So don't feel bad. But I think it'll be hopefully accessible. All right, so the P versus NP problem. This is a question about what makes certain kinds of problems easy to solve or quickly to solve on a computer, and other kinds of problems take a long time to solve on a computer, even though the computer is very fast. Okay? So we're going to start off slow with a nice, easy example. 7 times 13. So this is something we call multiplication. And if your arithmetical skills are rusty, the answer to that 7 times 13 problem is 91. Okay? Now, a related problem to multiplication is suppose I give you the product to start off with. I give you a number 91, which is, say, known to be the product of two numbers, but you don't know what those numbers are. And I ask you to figure out the two numbers that multiply together to give you 91. This is another computational or mathematical problem, and we call that the factoring problem. We start out with the product, and we try to figure out the two numbers that multiply together to give you that product. Okay, so in this case, the problem is 91, and the answer is 7 times 13. Okay, now let's take a bigger example of multiplication. So this is probably not the kind of problem that you can do in your head, at least if you're a normal person. But you can type this into a computer and even a laptop, push the, if you have the right software, push multiply, and the answer will pop out almost instantaneously. So this multiplication problem, even though it's for big numbers, will take because computers are so fast, even using the standard algorithm that you learn in 3rd grade for multiplying, it can run through the calculation very quickly and get you the answer in a second, or even less. Now, here is where it becomes interesting. Suppose I take that product, and I forgot the two numbers that multiply together to give you that product. And now I want to find those two numbers, just like we did before. This is a factoring problem. Okay, so here's the product, and I want to know what two numbers multiply together to give you that number. Well, you can solve that problem on a computer, just like we did for multiplication. And somebody actually did that. But here's the difference. Instead of taking a second for doing the multiplication, doing this factoring problem took 20 computer years of effort, 20 computer years of computer time. Now, they didn't actually wait for 20 years. They ran this on a highly parallel set of computers, so they were all a bunch of computers working together on this problem. But if you add up the total amount of computer effort that was involved, it was 20 computer years of effort to do this factoring. Now, first of all, you might ask, well, who cares? Why did somebody invest so much time to do this factoring? Well, people do care. And in particular, the person who did this exercise of factoring that number got $20,000 for doing that calculation. That's not bad. Now, you may ask, well, first of all, who's paying $20,000 to factor big numbers? And are there any other numbers out there that people might want to factor that we can also get in on this act? Well, let's take this number here. This is a $30,000 number. Okay, no one knows the factors of this one. Now, but who's paying? Well, first of all, I'm lying. The people who are paying decided to get out of that game. So we missed out our opportunity. That's no longer the payment for factoring big numbers has not. That's been discontinued. So, but still, people are interested, and mathematicians are work very hard on understanding how to factor big numbers. So, but still, who was paying? Well, there's a company called RSA Security, and they're involved with cryptography, sending encrypted messages on the internet. Your bank transactions, for example, in such a way that no one else can see what the transaction is or interfere with it. So there are cryptographic codes that rely on their security that rely for their security on the difficulty, on the presumed difficulty of factoring big numbers. If you were to be able to factor things quickly, then you would break that code. So the people who created this code and created that company are very interested to know whether people find fast ways of factoring numbers. And so I think to keep their kind of finger on the pulse of what's going on out there in the factoring technology world, they were offering these prizes. Now, they've gotten out of that business, but still, factoring is an important ingredient in modern-day cryptography, and that's where at least the practical interest in factoring algorithms for factoring comes from, though mathematicians have been interested in factoring for centuries. Okay, so what is so hard about factoring? What makes it different from multiplying? Well, when you're multiplying two numbers, you can, in a sense, construct the answer out of the problem. There is a procedure which constructs the answer. But when you're factoring a number, you want to find those two numbers that multiply together, the only way that people know how to solve that problem is essentially to search for the factors. No one has a procedure, essentially. There are little things that you can do, but essentially, no one knows how to factor numbers kind of by constructing the factors. The only way that people know how to do it is by looking for the factors. And when you have a big number, the number of possibilities you would have to search through in order to find the factors might be astronomically big. There are more possibilities than there are seconds in the lifetime of the universe or atoms, in the galaxy. So they were talking about such huge numbers that when you're trying to search through a space that's so long, it's going to take you a very, very long time. Because there are so many possible factors. So the question that we're interested in today is whether there is some other way to factor numbers that avoids that brute force search through many possibilities. Maybe there's another procedure for factoring that is more direct, that constructs the answer instead of looking for the answer. That's the essential question of today. Is searching necessary when you're factoring, or we'll see this comes up in many other problems as well, or is there some way to avoid searching in these kinds of problems? The answer to that question is at present unknown. Whether searching is necessary for certain kinds of problems like factoring. Okay? Let me give you another example. It's called the Klieg problem. So here you're given a bunch of nodes, we call them. They might represent people, say. And the lines or edges between the nodes might represent the relationships between the people. So you would say you put a line between two nodes representing people if these two people know each other. And now you want to go out for dinner. You want to get a group of people together, all of whom know each other. And here is your collection of friends, let's say. And you want to look in there for some group, let's say, of 3 people who know each other, because you want to go out to dinner. So here is a group. This group here, these 3, are what's called a clique. These are people who all know each other. They're all connected by these edges. But these 3 here are not a clique, because this pair here, they don't know each other. So for the purposes of constructing your dinner party, you're not going to invite them, let's say. So as a mathematical question, we abstract that into just this mathematical structure here, this graph. And we're trying to find these cliques. So here's a 3 clique, a 4 clique. These are all nodes that are all connected to one another. And you're given your collection of nodes, your friends, say, whatever. You want to see how big a clique you can find. Because you want to, make the biggest dinner party you can, let's say. So, it's easy to see we already saw that there were 3 nodes all connected to each other. There are 4 somewhere in here. I know that's true. These 4 here. This kite-shaped thing. These all 4 are connected. How about 5? Well, not so obvious, and turns out there are 5 that are connected to each other. These 5. I don't know if you can see that. Maybe this will help you out. So there is a 5 clique in this graph. And in general, we want to know, can we find a clique of a certain size, or what's the biggest clique in a graph? So, if you have a bigger set of friends, that becomes a more challenging problem to answer. And you can certainly do it by going through all the possible collections. If you want to say, well, I want to get together 8 friends now, to go out for dinner, but they all have to know each other, you're going to have to go through lots and lots and lots of possibilities in order to see if you can find those collection of friends which all know each other. At least as far as we know. Maybe there's some other way to solve this problem that doesn't involve going through all the possibilities. And if you have hundreds and hundreds of friends trying to find the biggest group that all know each other, the biggest clique here, might take centuries of computer time because there are so many possibilities to go through. Okay? And again, we ask, can you solve this problem in some other way that doesn't involve searching through all of those possibilities? We don't know. This is an unsolved question in mathematics and theoretical computer science. Okay? And this is the essence of what we call the P versus NP problem. These are both examples of what I would call, let me talk about this first, of the needle in the haystack problem. Okay? So I've actually, given this talk a couple of times, and sometimes there are a lot of people from other countries, and they don't know what hay is. So here, this is hay. This is stuff we feed to farm animals, and there is this needle in a haystack problem. Means you're trying to look for a needle somewhere in that stack of hay, which looks like a hard problem. Because finding the needle might involve searching through lots and lots of possibilities. You have to look at that piece of hay by piece of hay, one by one, seeing if you can find that needle. So that's another example of a searching problem in a kind of a practical case, not a mathematical case. Now, kind of abstracting it slightly, here's another picture of a haystack. And you want to know whether finding the needle in your haystack involves searching, or is there some way to do it without searching? Well, if you have a magnet, you can just pull that needle out without having to search for it. And really what we're asking here is whether there is, in those other problems that I just described, the factoring problem and the Klieg problem, is there a mathematical analog of the magnet? Some way which pulls out the answer without having to search for it. Okay, so this phenomenon is pervasive. It exists in hundreds and hundreds of real-world problems that people really care about. This question of problems that can be solved using searching, but that's too slow, so we'd like to find a faster way of solving them that avoids the search. For example, it's near the end of the semester, so it's time for final exams, and you'd like to try to find a schedule for the final exams so that there aren't too many students who have to take 2 final exams at the same time. That's called a scheduling problem, and there are many varieties of scheduling problems. Well, if you want to find the schedule that minimizes the number of conflicts, you can do that by searching through all possible schedules. That's, of course, astronomically big. And no one really knows, if you want to find the absolute best answer, of a way to do that that's faster than this brute force search through all possible schedules. So scheduling is an example of a searching problem. If you want to, for example, color a map, like you used to do, my teacher used to assign those when they did, when they were in second grade, when the teacher wanted to do something else, they would give these maps, and you have to color them in. Of course, 2 countries that share a boundary have to be a different color. You want to know, given a map, what's the minimum number of crayons you need to color the map so that you don't have any countries that border one another with the same color. So that problem, no one knows how to solve that problem in general, even for a map that you can write down on a piece of paper, a planar map, to minimize the number of colors without searching through all possible colorings. And again, so many, many colorings out there. Essentially. I mean, there are sometimes a few shortcuts you can do, but still the only way of solving these problems as far as we know, involves a search through a large space of possibilities. There are problems in computational biology. You want to see if you're given an amino acid sequence. You want to find the configuration that it folds into, which minimizes the total energy. Because presumably that's the configuration that exists inside the cell. Well, if you want to solve this problem in general, so that it works for any possible amino acid sequence, this is another case where finding the optimal folding involves searching through essentially all possible or many, many possible foldings. And there are so many of them. There is theorem proving. I'll talk about that more in a second. Variety of puzzles, Sudoku and so on, traveling salesman problem. There are hundreds of these, maybe thousands, where problems that you can solve them by searching, but it's very inefficient, it's very slow, and no one knows if there's a better way. And that's the essence of this problem called the P versus NP problem, P versus NP question. Can we solve these problems which seem to involve searching, but without actually resorting to the search? Can we solve these apparently search problems in a more direct way than actually searching? And so that addresses all of those problems that we just discussed: Klieg, factoring, protein folding, and so on. This phenomenon appears in all of them. OK, let's just talk for a minute about, this is not essential to understanding the presentation, but let's just try to define the terms here. P stands for the polynomial time. These are the problems that you can solve in a number of steps that grows only as a polynomial in the size of the problem. Solving a problem by searching for the answer will in general require an exponential number of steps. So these searching procedures are not polynomial time procedures. So the polynomial time class of problems are the problems like multiplication, where you can solve them without searching. But whether, for example, the Klieg problem is in polynomial time is not known. Because if it were, then you would be avoiding the search for the Klieg problem. So these are the problems that can essentially be solved without searching, because searching is too slow to operate in polynomial time. Now, NP is a slightly more complicated notion. These are problems where you may not necessarily be able to find the answer quickly in a polynomial number of steps in the size of the problem, but you can check the answer quickly. So let's understand what that means. Like in the case of factoring, there is something interesting about factoring, because even though it might take you a very long time to find the factors because of that brute force search, once you've found them, you can easily check that you got the right answer by multiplying them to see if you get the starting point. Similarly, if your Klieg problem is, well, does the graph have a Klieg of size 20? It might take you a long many steps to actually to run through all the possibilities and find such a Klieg. But once you actually found one, it's easy to check that it works. So there are many problems that have this character that it seems like you need to search for the answer, but once you find the answer, it's easy to check that it's right. That's the essence of NP. These are the quickly checkable problems as opposed to the quickly solvable problems. And they include all the search problems that we just mentioned. OK? So just in terms, thinking about it in terms of like a Venn diagram of classes of problems, so these circles here represent whole classes of of computational problems, like factoring, Klieg, traveling salesman, and so on. The P problems are the ones that are easily solvable, like multiplication or sorting or any of those problems where you can get the answer quickly. whereas NP are the problems where you may need, where the answer, once you find it, is easily checkable, but actually finding the answer might involve searching for it. So these are really the searching problems out here, and these are the problems that can be solved without searching. So if it turns out that that we can always eliminate searching, then these two classes would collapse down and be the same. Right? If you can always eliminate searching for these problems that are in NP, then they would collapse down and become P problems, problems that you can solve quickly. And so then P would equal NP in that case. But if there are certain problems in this class which really require searching, then they would not be in P, and you would have P different from NP. Okay, so that's a little bit on the technical side, but that's where this terminology comes from. The P versus NP really amounts to, does P equal NP, which means you can always eliminate searching, or P is different from NP, which means that sometimes searching is essential, cannot be eliminated in some cases. And the answer as to which of those cases is the actual reality is not known. Okay, that's the P versus NP problem. So let's talk a little bit about the history of the problem, because it's interesting. If you go back to the 1960s, that was when the whole subject of complexity theory got set up. Some of these folks are my teachers. In the early 70s, the P versus NP question was first formulated, and its companion notion of NP completeness was proposed. We'll talk about that in a second. And I'm very pleased that Dick Karp, who introduced me, was one of the key contributors to this whole development. But one thing that was discovered, I don't know, now it's been 15 to 20 years ago, is that there was actually a precursor to the whole thing that appeared in a letter Kurt Gödel, the great logician, wrote to the mathematician John von Neumann. So there was a letter which foreshadowed the whole development. And it appeared back in 1956, almost 10 years before any of this appeared in the literature, which is kind of amazing. So I thought I would just show you the letter here. Here it is, in fact. It's a little hard to read, not only because of the printing is small, but it's in German. And it was found in von Neumann's archives, something around, I don't remember exactly, but around 20 years ago. I thought I would just translate a few bits and pieces of it, just because it's interesting to see the language that was used. And actually, for those of you who know something about the subject, what's amazing to me, anyway, about this letter is the modern terminology that he uses much before any of this appeared in the literature. Oops. Oh, yeah, here's the letter. I want to tell you first who these people are, in case you didn't know. Kurt Gödel was, many people think of him as the greatest logician who ever lived, or the greatest logician since Aristotle. You know, he was an amazing person who did all sorts of stuff in mathematical logic. And among his many accomplishments was sort of this understanding of this question about computation, which was only known by virtue of that letter that appeared in von Neumann's archives. John von Neumann was a great mathematician who worked in a whole variety of fields. He is known in particular for having worked in computer science. He was an early computer pioneer. He's known for the so-called von Neumann architecture. I don't know if he was actually the only one to think of that concept, but this notion that you can store the program of the computer in the computer itself. So let's turn our attention back to this letter. So the letter starts off, and I'm translating little bits and pieces of it. Lieber Herr von Neumann, that's the opening here. Dear Mr. von Neumann, Princeton, March 20th, 1956. Kind of a curious side note is that both Gödel and von Neumann were at the Institute for Advanced Study at the time, presumably down the hall from one another. So why exactly Gödel wrote this in a letter to von Neumann, I do not exactly know, but you can make, maybe he just wanted to get it down in print, or maybe, von Neumann at the time actually was rather sick, He was dying of cancer, died less than a year later. Maybe he just was not, maybe he was hospitalized. I actually don't know. But in fact, the whole beginning part of the first page of the letter talks about how Gödel is aware that von Neumann is unwell, and he hopes he gets better. And he says, at the end of the first thing, he says, well, now let's turn to some mathematics. And here, then, he talks about, here is really, what he's asking here is, I have to explain this. He's talking about the problem of how hard it is for computers to test whether a mathematical statement has a proof of a certain specified length. Okay, so you give a length n, and I want to know, you give a length n, you give the statement, and the computer is supposed to check, does that statement have a proof of length n? Now, if you eliminate the n, if you say, does the statement have a proof at all, we know that's not solvable by computer. That was actually derived from some of Gödel's work himself. But if you put the bound on, if you say, does it have a proof of length n, well, of course, it's now solvable, because you can just try all possible proofs of length n and, and see if any of them are legitimate proofs of the statement you're trying to prove. It's a finite problem. But that's a searching solution. You have to search. That procedure involves searching through all possible proofs of length n, and there are so many of them. So what Gödel is asking here is, how much time does it take to test, this is his function phi of n, that's how much time it would take to solve the problem for proofs of length n. How long would it take if you have an optimal machine instead of just the brute force searching machine? Maybe there's some better way. So how long would an optimal machine take to test if your statement has a proof of length n? This is the P versus NP question right there, formulated in a slightly different language. But this is really the P versus NP question. We might quibble slightly, but this is basically it. Then he goes on to talk about Blossen probieren, which is, I'm told, I'm not a German speaker, but it means blind probing, which I think loosely is brute force search or exhaustive search. That's searching. And then he goes on to talk about other problems besides testing whether a statement has a proof of a certain length. He talks about testing if a number is prime. Or, in general, other finite combinatorial problems. He doesn't specifically mention Klieg, but I think that's the kind of problem he has in mind. So we really hear in this letter, he actually has carved out a vision for where the field ended up going. I think it's an amazing discovery in the history of science that this letter was found in von Neumann's archives. Anyway, and then he signs it at the end, Kurt Gödel. So, in the years since Gödel's letter, there's been a lot of literature, and the whole subject has developed, and this problem now has become celebrated as one of the it's probably the greatest unsolved problem in theoretical computer science, and it's considered one of the great problems in contemporary mathematics. So there are these, some of you may know, there in the year 2000, there were these Clay millennium problems posed. These are supposedly 7 unsolved problems put together by a committee, inspired by the Hilbert problems, if you've heard of those, but it doesn't matter. They were a century earlier, but these were put together in the year 2000, kind of as challenges to the mathematical community for the coming century. And as you can see, the P versus NP problem was one of those 7 grand challenge problems in mathematics. One of these problems has a check mark next to it, because that problem actually was one of these 7 grand challenge problems that's already been solved. So these are not impossible problems. They can be solved. That Poincaré conjecture was 100 years old when it was solved, and there's a whole story behind it. The guy who solved it was a little bit strange. He, I should mention one difference between the Clay problems and the Hilbert problems is that there's a $1 million bounty on solving any one of these problems. And the guy who solved the Poincaré conjecture didn't want the $1 million. He said, what's $1 million compared with the glory of solving the Poincaré conjecture? Which I can understand. This is a problem, for the ages, and how does that How does $1 million compare with that? So all right, let me tell you, now, you know, I've spent a lot of time thinking about the P versus NP problem. People know that it's a problem I'm interested in, and lots of people send me solutions. I get phone calls, I get letters, and so on. And you know, many of the solutions I'm really kind of simplifying, but it's actually true. They kind of, some class of quote solutions amounts to essentially, well, these problems are searching problems, and of course you need to search to do searching problems. The end. So what I want to show you here is that it's not so simple. You know, testing if a number is prime looks like a searching problem, right? You have a big number. You want to know, is it prime? Does it have any non-trivial? Does it have any factors, you know, besides 1 and itself? So can you actually factor that number in some interesting way? I think most of us know what prime numbers are. And you want to know, you want to test if a number is prime. So one way to do it is by searching. You can search for factors, and if you don't find any factors, then you know it's prime. But there's another way. And let me give you a taste of how that goes. It uses some number theory, but not, at least at the very most elementary level, it's not, you know, it's sort of understandable. So here's a strange way to test primality, and it's based on this following principle that's going to ultimately be used to avoid the searching. It relies on this old theorem due to Fermat. It's like, you know, it's not Fermat's last theorem, it's another theorem that he actually did prove. It's the following simple statement, but you have to bear with me on this. This is as technical as the talk gets. Okay, it's not that bad. If I have to take a prime p, any old prime, like 7, and I take any number from 1 up to p minus 1, so any number that's less than p, call it a, like maybe 2. If I take that number a and I raise it to the p minus 1 power, and then I divide by p and take the remainder, that's what this means, mod p, divide by p and take the remainder, I always get 1 coming out. It's kind of amazing when you actually try it in practice. Why in the world should that be? Well, Fermat proved it. It's not actually that hard to prove. But let's just illustrate this with an example. Okay? So let's take the case I mentioned. P equals 7, A equals 2. Okay? So you can take 2 to the 6th power. That's A to the p minus 1. 2 to the 6th power. That's 64. Okay? Now divide by 7. Well, 7 goes into 63 evenly. So the remainder, when you divide it into 64, is going to be 1. Of course, this is no proof. This is just an example. But it always works. Now, contrast that with what happens if you started with p equal to 15, which is well known for not being a prime number. Okay, so p is, we start with 15, a non-prime. Let's try plugging in the same thing, see what happens. Well, you take a equal to 2 again. Now you get 15 minus 1. P minus 1 is 2 to the 14th. That's this number here. And if you divide by 15, you get a remainder of 4. And 4 is not 1. That tells you something. It tells you that 15 is not prime. Because this calculation resulted in a number other than 1 here, it resulted in 4. I have just proven to you that 15 is not a prime number. Of course, we knew that, right? But it proves it in an entirely different way. It says that 15 is not prime because it fails to have a property that all prime numbers have. And so therefore, it couldn't be prime. It doesn't say anything about 15's factors, by the way. And this is kind of the starting point for a procedure that allows you to test primality. First, there was a procedure that worked kind of with a randomized, and then ultimately the randomization was removed. And so primality testing is now known to be solvable in polynomial time. So you can cut out the searching entirely. Using this, this idea is the starting point. Okay, so I mentioned this notion of NP completeness. Okay, so NP completeness is probably, well, perhaps it was a very important early development in trying to understand this whole phenomenon of P versus NP. And what it tells you is this, that we have all of these searching problems, like factoring, Klieg, and a variety of others. But it turns out that in many cases, the question of whether or not these problems require searching is related to each other. So let me say that slightly better. What we can show by virtue of this NP completeness method is that if I can find a procedure which solves the Klieg problem without searching, so a polynomial time algorithm for the Klieg problem, if I can do that, so if I can get rid of searching for Klieg, then I can get rid of searching for factoring. You understand? This is kind of a miracle. What does factoring and Klieg have to do with each other? But by eliminating searching from the solution to the Klieg problem, I immediately get a way of eliminating searching for the factoring problem. So how in the world does that? How do you prove that? Because this is known. It's because there is a way that you can demonstrate, and this is very concretely done. Too complicated for me to say here, but at least the idea I can say. You can convert factoring problems into Klieg problems by a transformation that itself is fast. So in other words, I can kind of hide a factoring problem as a Klieg problem. I can encode it as a Klieg problem. So now if I can then solve Klieg problems without searching, I've solved my factoring problem because I represented my factoring problem as a Klieg problem. So I've kind of illustrate that here. Okay, so that's the idea. I can convert a factoring problem into a Klieg problem and then solve the Klieg problem. That's the essence of NP completeness. And, well, one more point is that Klieg is a special problem because every NP problem, every one of these problems that has easy checkability, as we mentioned at the beginning, can be transformed by some fast transformer into a Klieg problem. So we say that Klieg is NP complete. So in other words, if you can solve the Klieg problem fast, you can solve every NP problem fast. So Klieg is special. And many problems in NP are known to be special in that way. Those are called NP complete. And therefore, if you can solve Klieg in P, then every NP problem can be solved in P. You can always eliminate searching for these easily checkable problems. So you've kind of focused the entire complexity of this class of NP problems onto a single problem, the Klieg problem, or any one of the other NP complete problems. OK, so now, OK, so this is kind of gives the sense. These NP complete problems are, in a sense, the hardest, because if you can solve any one of these, you've solved them all. OK? Now, I thought I'd mention, too, just sort of getting a little bit into the home stretch of what of my lecture, that the world is a complicated place. There are certain kinds of search problems which seem to transcend even NP. These are searching problems where once you find the answer, you don't necessarily have, as far as we know, an easy way of checking the answer. And I'll give you, just to illustrate that, it's the problem of testing which side has a forced win in a game like chess or any of a variety of games. If you, and you have to, I know for the experts on there, you have to talk about generalizations here, but let's just be loose. In a game like chess, if I want to know what's the outcome if both sides play optimally? Does white win? Does black win? Or is it always a draw? Under optimal play, if both sides were the best possible players. No one knows the answer to that. But you could find it out using a computer that would search through the entire tree of possibilities. So there is a kind of a searching procedure, because the tree is astronomically big. You'll never be able to do it in the lifetime of the universe. But in principle, you can get the answer. And suppose you determine by searching this tree that white does in fact have a forced win. How do you check that? No, that's not something we know how to do. So this is a problem which is a searching problem which seems even outside of the NP class. It's a searching problem that doesn't have this easy checkability as far as we know. And this is one of these, well, as far as we know. OK, so just to give you a sense of the lay of the land, in the many years that complexity theorists have been looking at these kinds of things, they've placed these problems here. Optimal games is in a class called polynomial space. These can be solved with a polynomial amount of memory, not necessarily a polynomial amount of time. Here are the Klieg and factoring problems in this NP class, as we saw. Here's multiplication down in the P class. But complexity theorists have been hard at work trying to come up with other methods of categorizing problems in a natural way, almost like the periodic table in some loose sense. So there's a variety of different classes out there that people have discovered corresponding to classifying problems in different ways. And the whole subject is still evolving. So if you focus here on, for example, the primality problem, it used to be up here in this RP class, which stands for randomized polynomial time. But about a dozen years ago, a procedure for eliminating the randomization was shown. So it's fairly recently, this picture has changed. And other changes are possible. So, so we have this unsolved problem, P versus NP. How might we actually answer it? Of course, I don't know. But we can speculate. One possible method that suggests itself would be, you want to show that there's no clever way to solve a problem like the Klieg problem. You have to search. If you want to prove P is different from NP, which is what most people believe, not necessarily everybody, but most people believe P different from NP, that these problems really require searching, then for you, a fast algorithm is kind of your adversary. You want to prove that there's no fast algorithm for the Klieg problem because you believe searching is necessary. So the fast procedures are kind of the bad guys. You don't like the fast procedures. You want to show there aren't any of those. So this is the fast procedure which is claiming to solve the Klieg problem. But the problem is that fast procedure can be very clever. It can do crazy things like that procedure for testing primality. All sorts of things that who knows what it could do. So one way perhaps is to get a handle on it by limiting the class of procedures that you'll allow. You handicap the computer. So you take it with a stick, you hit the computer, and so now the computer, instead of being able to run, can only kind of limp. And maybe now you can prove the computer has to take a long time to solve the problem because it's limping. If that doesn't work, you give it another whack. Now the poor computer can only crawl. Eventually, enough whacks, you can prove something. And then maybe you can start to relax some of these handicaps that you put on the computation, and you learn something about what it takes to show that there are no clever algorithms. All right, another possibility would be you want to take your algorithm, which supposedly is working fast for the Klieg problem, and you want to somehow find a very complicated input. And say, on this input, it's going to have to take a long time. If you want to find a complicated case, it's sort of natural to work with a very big instance. The bigger the problem, sort of the more complicated it is. And to a mathematician, that sort of suggests, why don't we take that to its most extreme? Let's try to give it an infinite input. Whatever that means. Okay, try to make sense of that and to show that maybe on this infinite input, it's easier somehow to say that the machine has to take a long time. Again, you're not clear what these means, but you can make some sense of these things. Okay, but none of these approaches have panned out in the end, unfortunately. And so, you can ask, well, will the problem ever be solved? I believe it will, but we'll certainly need new ideas to do so. Thank you. The question is, if you want to code up a factoring problem into a Klieg, how big, if you start out with a factoring problem that's 100 digits or n digits long, how big a Klieg do you end up? This is not the kind of thing I'm all that good at, but let's, so what's, the problem, multiplication is, that's a pretty, it's going to be something like n cubed would be my guess. It might be n to the fourth, it might be n squared, but it's in that range. That's how big. Is it bigger than what? Oh, yeah, you'd have a, yes. So, for a number of length n, you would have to end up with a Klieg, which would have, millions probably, maybe even tens of millions of nodes. But hopefully that's not so bad if you have millions of nodes, if you have a procedure that doesn't involve searching. Of course, there's a lot of shades of gray in this whole conversation which have conveniently left out. There are big polynomials and small polynomials. When you say polynomial time, that doesn't necessarily mean it's practical. There are procedures that run in polynomial time, but still fairly slow. But nevertheless, the question of polynomial versus exponential or searching, exponential versus polynomial or searching versus non-searching, that's a kind of a litmus test that's often used for practicality or impracticality.
The first panelist to speak will be Christos Papadimitriou.
So computation is something extremely practical and worldly. So it must be interesting for that, okay? And frankly, I don't think so. Okay, the reason why this is an interesting question, I think, is much more basic. There are some questions that you cannot dare not call important. How about is there a single equation that governs the cosmos? What was the origin of life? How did life begin on Earth? Okay, so if you want to argue that these questions are not important, I don't want to argue with you. Okay, so and I believe that P versus NP is can exhaustive search always be telescoped? Okay, how can you not try to answer this? How can you not want to know the answer to this question? If we manage to live on this planet for a couple of thousand years more, and we are not able to answer this question, what's the point? Okay. The other thing, is what does P versus NP and NP completeness means in practice? Okay, because many of you may know that there are practitioners who come and tell me and tell everybody, all of us, these NP complete problems, I solve them, thousands of them every day. So my company depends on it. Okay, so I solve them. So you see, people are very clever, very innovative, very versatile, and essentially they can live with anything, including NP completeness. Okay, so they find ways around even the extremely hard problems, right? The point is the following: that when a problem has been proven NP complete, it's not like it will never be solved. It will be solved, okay? But you have to change what solution means in order to solve it, okay? The solution cannot be clean, cannot be satisfying, okay? Cannot be, when you actually prove a problem to be in P, when you develop a polynomial time algorithm for a problem. That's really amazing. Okay, so you really have done a good day's work. Right? There was this man called Jack Edmonds, who is his time in the 60s, he found these amazing algorithms for some very, very complicated problems, okay, polynomial time algorithms. I know for a fact that he was very satisfied that day. Okay, I know, he slept very well that night. Okay, so ultimately, P versus NP then is about peace of mind and a good night's sleep. Okay.
I neglected to introduce Christos. Christos is a long-term colleague at University of California at Berkeley and a Princeton PhD from 1976. Our next speaker is Omer Reingold, who is at the Mountain View Laboratory of Microsoft and received his PhD from the Weizmann Institute in Israel.
Before I start, just one sentence to complete Christos. Even if we don't solve, a great problem is one that even if we don't solve it, we get so much on the way. And I think this is true for all the other problems Christos mentioned, and I think it's also true for P versus NP. And we didn't only spend decades not solving it. But I want to claim now that if I'm taking a physical kind of an analog, when you want to learn about computational hardness, computations and what's hard, we need to view it in all ranges. So from the stars and the galaxies all the way to the atoms and the particles. And the questions kind of down there is, how does hardness form? How does things become hard? And are there any things in the range between things that we cannot solve and things that are very easy? And I'll try to give very quick examples for that. The first one is something called pricing via processing, an idea from 22 years ago for fighting spam, which I think can be found its way to things like Bitcoin. And this is the point of, okay, what's the issue with spam? Spam is very effective because emails are very cheap. So if you send your email to 1 million people and only one of them answer to your Nigerian scam, this is still worthwhile. So perhaps an approach is to make email a little bit more expensive. And here is an idea. Whenever I want to send somebody an email, I'll have to, in return, solve a very simple problem. For example, one Sudoku problem, which turns out to be also NP-complete. And now, when I solve it, with my email, I'm going to send the solution to the problem.